Right, welcome back. So, a little different this time. So I thought lots of people have trouble setting up Dshot for ArduPilot. So I thought I'd take you through that briefly, but then going to show you what the different options do and explain a little bit about Dshot along the way. So to do that, I've got my trusty logic analyzer here, and I'm hooked up to a Maytech, you should be able to see in Mission Planner here, Maytech H743 Slim, and what I'll do first is show you what, so the basic setup for Dshot is this MOT PWM type, and by default this is set to 0. So when you load up ArduPilot, so if I reboot this, so we should be able to start this and have a look. Okay, so this is my logic analyzer, and it shows highs and lows, and this is the analog. You can see here is the lower one, and the digital output is the top one, so you can see they're roughly equivalent. And this is what PWM looks like. So this is pulse width modulation, so it's the width of the high part of this pulse that determines the output in PWM, and typically measured in microseconds. So you can see that we've got 1 millisecond high, 2.5 milliseconds low, so that makes 3.5 milliseconds. Sorry, so this makes, so 1 millisecond is about 1,000 microseconds. So this is the equivalent of 1,000. When you see a PWM value of 1,000, that's what this means. This is a PWM value of 1,000. Now you may be able to hear my ESC beeping in the background. It's AM32, and I don't think AM32 supports PWM, so that's why it's not arming. So that's what PWM looks like. You see 1 millisecond, 0.5 milliseconds. And what we want to do is set up Dshot. So let's change this to 6, MOT PWM type to 6. So this is, so that's Dshot 600. If we reboot, and now my ESC is happy because it's seeing Dshot. So Dshot 600 showing here, and if I look, if I run this again, okay, so this time, so this is the same scale, so you can basically see that the pulses are a lot narrower. So those were, if you remember, 1 millisecond. So now let's dive into one of these pulses. So here is a Dshot pulse, and we can measure this at a timing marker from here. Whoops. Here. Delete that again. It's all right. Add a marker pair. Okay, so from here to here is 6.7 kilohertz, and this marker is 26 microseconds. So you can see there's 26 microseconds across that pulse, which is considerably quicker than PWM. Now, if we delete that marker, now if we dig in a bit more, so you can see that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 of these pulses, and what that is 11 bits, I think it's 12 bits of data and 4 bits of CRC. So these last 4 are the CRC, so that's checking that the data is correct, and these first 12 are the actual data value. And Dshot looks a bit like PWM, so each of these has a low time and a high time. Now, in PWM, it's the width of this high pulse that determines the value. But in Dshot, each of these pairs represents a 1 or a 0, and so you can see that you've got a narrower high time and a wider low time, and that represents a 0. If it was the other way round, so a wider high time and a narrower low time, that would represent a 1. And you can imagine that with sort of 12 bits of data, you can represent numbers. So it's 12-bit numbers basically represented by these 1s and 0s, and that's what gets interpreted by the ESC. Now, the next thing to notice is there's 2 sort of timing values here. So there's this gap between each Dshot pulse, which here is sort of between 300 and 150 micros, and that is the output rate. So that's the rate at which the flight controller is sending Dshot pulses, and that's nothing to do with Dshot 600, Dshot 150, whatever. That's purely an output rate. So 300 microseconds is so if this was 1,000 microseconds, that'd be 1 millisecond, so that'd be outputting at a kilohertz. And so this is outputting closer to sort of 3 times that, and there's a reason for that. So if we go back to our thing here and look at servo Dshot rate, you'll see that we've got loop rate. It's set at the loop rate. And what is our loop rate? Well, we've got the fast rate loop running. So this is trying to output at the gyro rate. So I'm going to turn that off. So no longer got the fast loop running. And I'm going to look at scheduled loop rate. So let's make this the default 400. Okay, so scheduled loop rate of 400 Hertz is the default loop rate, and the default for servo Dshot rate is 0. So that's what the board would come initially configured with. So if we reboot that. Okay, so there we go. So let's go back here, start this up again. See what we've got. All right, so we've still got pulses appearing. What do they look like now? Okay, so now you can see that the gap between the pulses is much wider, and it's approximately a millisecond. So approximately a kilohertz output. And some of these are a little bit narrow, but most of these are about a millisecond, 977 micros, which if you add on the sort of 30 odd micros for the pulse width gets you to about a millisecond or 1,000 micros. Now, that width is because we set this D-Shot rate to 0. And if you don't set the D-Shot rate, then the output rate is fixed at 1 kilohertz, which is what we're seeing. So let's change that. Okay, so let's change the D-Shot rate to 1. So that means run output D-Shot at the scheduled loop rate. So let's do that. Don't think this updates dynamically. Nope, doesn't. So we'll have to reboot. Lots of rebooting required. All right, it's rebooted. Let's go back here. Okay, so what have we got now? All right, so look, so these pulses, so two things to notice about these pulses. One is that they're completely even now. So there's no variation in the pulses. And they're each 1.2 milliseconds apart, 1.22, 23. And if we divide 1,000 milliseconds in a second by 1.22, we end up at 800, which is odd. Because the output rate. Okay, so I know what's going on here. So the rate is constrained to be 800 at the lowest in the code. So you can never go below 800 hertz, and this is because some ESCs we found just don't work if you send data too slowly. Now, Betaflight sends these pulses at like 4 kilohertz, much faster. So 800 hertz is already pretty slow. Slower than that would be pretty bad. So that's 800 hertz. It's constrained to 800 hertz. But let's play with it a little bit and okay. So our loop rate is 400 hertz. So if we set servo D-Shot, so if we set servo D-Shot rate to 2 times 400 hertz gives us 800, so we get the same value. All right, so let's set this to 4. So this should output at 1.6 kilohertz now. So write that parameter out. Reboot again. And we can start this. See nothing coming out. Well, and there we go. Right, so now what do we got here? So now you can see that there's a roughly 600 microseconds gap between D-Shot pulses. And roughly 600 microseconds gap is 1.6 kilohertz. So that was what we're after. So now you can see the effect of servo D-Shot rate. And this sort of achieves a couple of things. One is you can get these very even pulses going out based on your loop rate, and the other is you can play with this, make this faster or slower. Sometimes faster, the ESCs are a bit happier with it, but also when you can only get telemetry at the rate that pulses go out at. So if you start to use something like BD-Shot, which allows telemetry to come back, this allows you to get a faster telemetry rate from your ESCs. So there's a couple of reasons why you might want to play with that. Alright, so I'm going to set this back to 3. So it's about 1.2. That should be about what 400 times 3 is 1.2 kilohertz. Reboot Pixhawk. Let's see this going again. Alright, so it started. Okay, and now you can see, oh, there we go. Alright. Interesting. So interestingly, the ESC is not very happy with that pulse width rate, so you can hear it finding and losing the pulse. So it's going at the right rate, 800 hertz, but maybe a little bit too slow for AM32. May just be that it needs rebooting. I shall try that. No, it really doesn't like that. All right. So, Dshot rate of 3, not so good. Okay, so let's get this going back up to 4. Whoops. Need to be connected. So, Dshot. All right, set that to 4. Reboot. Okay, oh, it's back again. And, okay, so the AM32 nonsense has gone away now, so that's great. So it's able to process that, and you can see we've got these, again, these 600 microseconds differences. So AM32 likes the update rate to be a little bit faster. Okay, so that's servo Dshot rate and its relationship to shed loop rate. So what about the actual value of Dshot? So we've got, let's go back to this pulse. So if you remember, this pulse is, let's just measure that again. Okay, there we go. So that's about 25 microseconds, and it's about 600 kilohertz. So this is the actual Dshot rate. So Dshot 600 means 600 kilohertz, and it's this bit rate that you see here. So 25 microseconds, 600 kilohertz. So what we can do, let's get rid of that. Let's change this to MOT PWM type. Let's go for 4, which is Dshot 150. All right. Okay, so I've got to reboot that. Oh, I don't think it's interesting. So you can see that, so we've still got this bit, this pulse width, but now if we have a look at the width of this guy, Right, that's now 100 microseconds, and the output rate is 150 kilohertz. So that's where the Dshot 150 comes from. But you can also hear that AM32 is not very happy with that as a rate. So something to do with the rates that we've set. So we could try, let's try Dshot 300. There we go. All right, so Dshot 300 it's much happier with. Dshot 150 it wasn't happy with. So let's have a look at these pulses again. So you can still see that the width between the pulses is still roughly 600 microseconds when we add in the pulse width. And if we look at an individual pulse, let's do a measurement across here. Right, now you can see the pulse width is 50 micros and 300 kilohertz. So this is Dshot 300, so the bit rate is 300 kilohertz. So that sort of explains the different output rates. So now that's the basic setup for Dshot. So pick MOT PWM type, probably 600 is probably the safest thing to do. And then you can play with servo Dshot ESC, sorry, servo Dshot rate to make the output rate a multiple of your scheduled loop rate. All right, so that's Dshot. Okay, so what you'll see is that the Dshot by default, the line is low, and so it's active high. Now, typically we want data coming back over the Dshot signal lines so that we can set our harmonic notches in, and this is where BDshot comes in. So I have this firmware I've loaded up is the Matex Slim BDshot version. I don't know if you can see it just there, BDshot. And if you have the BDshot version of the firmware, not all firmwares have different versions for BDshot. Some firmware supports BDshot out of the box. But what we can do is we can now set a mask on servo BLH BD mask. So this is the mask of channels that you want bidirectional Dshot on. So it's a bit mask, and so for a normally for a copter you have first four channels, 1 to 4, and since it's a bit mask that means the first 4 bits are set to 1, which means the actual value is 15. So I'm going to set that. Now, Mission Planner helps you with the little channel, so if you click on the set bit mask, it'll show you the different channels, and you can click the individual bits. And so, for instance, for a cube or something like that with an IOMCU, the channels that support BDshot are all indexed from 9 onwards, and so you have 4 channels from channel 9, 10, 11, 12. It gives you a value here of 3840. So this can be quite hard to set if you've got a flight controller with IMCU on it. But for regular sort of 30 by 30 boards, it's relatively straightforward. So okay, so I've set this to BD mask, and then the other thing you've got to be careful of with BDshot is this value of poles. So this is the number of magnetic poles in your motor, and typically when you look at a motor spec, it'll tell you the number of poles. So it'll say something, a number followed by P for the kind of configuration, and that number is the number of poles. For these sort of smaller motors, 14 is the normal value, but you can get ones that are 12 for Whoop type motors, or you can get ones that are 28 for larger motors, for larger copters. So we want these 2 values set. So we set all those values. Alright, so now we are going to reboot. Okay, and we'll set this going again. Alright, now, so if you remember we had active high. Now you can see with Dshot we have active low. So we've still got this roughly 600 micros between the pulses, but let's have a look at the pulse. Okay, so in the pulse you can now see that there's two bits to this pulse. There is the outgoing value, the outgoing Dshot value, and then there's the incoming telemetry value. And with this outgoing Dshot value, there is, so we've got active low here, and so everything's inverted, and the encoding is a little bit different. So you remember there was sort of 12 bits of data plus 4 bits of CRC. You can now see that the way Dshot is encoded, the CRC is kind of inverted. So you can see the CRC, these last 4 bits have the opposite pulse width to the first set of bits. Now it's Dshot. We're running at 300, so the width should still be the same. Oops. Add a measurement. Okay, so here we go. Here's a width. And so you can see that's still 300 kilohertz, still roughly 55 micros. So it's still Dshot 300. But then we've also, after this guy, whoops, let's just measure this. So we can just see there's a little measurement here. So 25 micros. So after 25 micros, the ESC sends back some data. And you can just see also there's this little, so on the digital output we've got this little spike down, and there's this little glitch here. We zoom in a bit. And I think so this is not data at all. What this is when the flight controller switches from output to input, and we get this little tiny glitch there. And so once it's done all its output, it can switch to input, and then after the input data can be read here. And you can see that we get a telemetry packet for each Dshot pulse that we send out. And so you can see why setting survey Dshot rate might increase your telemetry rate, because we will just basically get extra of these. And that's kind of all that, well, it's almost all there is to say about Dshot, because once you've got the telemetry running, it's kind of what you need. And now, the other thing to say is that these AM32 ESCs and some of the modern, so BL-Heli 3210 and Blue Jay, support this thing called EDT, which is Extended Dshot Telemetry. And what EDT is, EDT basically allows you to send extra information in this telemetry packet back periodically. And in particular, so this is basically RPM, but in particular voltage, current and temperature. And so we can enable EDT by going to Survey Dshot ESC. By default this is 0, which basically means don't set anything. But we can set this to 1, and that means, sorry, not 1, set it to 3, which means support EDT for BL-Heli and AM32 ESCs. And if we then reboot, Okay, so we've got Dshot again. What we might be able to see is, you can see here, if you have a look at the pattern, it's probably not that easy to see. I'm just seeing whether I can see one. Can't find one. So I'm looking for a telemetry packet that's not RPM, and usually that will have different values in it, but these all look the same, and there are thousands and thousands of them, so I don't propose to go through all of them. But if we look at our status, look at the ESC information, here we go, ESC, oh, well, maybe that's why, because there's no EDT information coming back, which I don't know why that would be. Just check I've set this up correctly. Server Dshot ESC. Yeah, no, I've set it up correctly, so I don't know why that is. For some reason, we're not getting ESC voltage or current here, and I would expect us to. I could try rebooting. I could try repowering. I'll just try repowering just in case it's something to do with the ESC. Right, let's see whether that improves things at all. Nope. All right. So for some reason it's not sending EDT information back. If I did this with BL-Heli, you'd see it, but I don't know why that is. Something to do with this test setup I've got. And then the final thing to say about that parameter, so I've got this servo Dshot ESC. So this parameter, so you'll notice that there are other values for Blue Jay, and there's none, and so the sort of this parameter is sort of multi-pronged. So by default, 0 gives you default timing. If you set this to 1, basically it says I know that this is a Dshot ESC, so I'm going to send Dshot commands to make some of the other parameters work. So basically, I've set this to 1. This means Dshot commands now work. And if I go to servo BLH, so this value RV mask, reversible mask, if I set some of these bits, basically the flight controller will send the command, the Dshot commands, to reverse the motors that you request in this mask. So instead of having to do it on the ESC configuration side, you can do it direct from the flight controller. So that's what Dshot commands give you. And Dshot commands also give you sounds. So if you go to NTF buzzer types, okay, so the NTF buzzer types is set to 5. Can't see my little thing here, but there's a buzzer types which includes Dshot, which is bit 2, and so if you set this to 7, NTF buzzer types to 7, you can basically use Dshot commands to play little sounds through the motors. And if your ESC support LEDs, same thing applies. So So that's Dshot commands. Now, if you select BlueJ, that will still support Dshot commands, but it will slightly alter the timing of Dshot timing. Not the space between pulses, but the actual widths of the pulses themselves. It will alter that to support timing that BlueJ seems to find more acceptable. And this is one of the challenges with Dshot, is all of these ESC implementations are different. And although it's all supposed to be relatively standard, there seems to be some vagaries in the timing between different firmware, but also different hardware that the firmware is running on. And so if you've got BlueJ ESCs, you can set that to 2 for BlueJ. And then EDT 3 is EDT plus BLHeli-M32 type. And then 4 is EDT plus BLHeli-S and BlueJ type. All right, so that's the various Dshot parameters that you can play with. Hopefully it educates you a little bit more about Dshot. Give it a go. Thanks for watching.